now velocity distribution in open channel. As I told you initially, the velocity distribution in this open channel will vary with the depth, and that is the logarithmic distribution, or you can call the power law distribution up to a maximum velocity point. See, this is your logarithmic variation and in terms of your power law distribution, and the maximum velocity little bit below the certain depth of your water surface. So this is called your dip. The dip due to your wind shear. We can ask in the examination, this dip is due to the wind shear and it is a function of your aspect ratio. Aspect ratio is ratio of your depth to width of your channel. This is the most important thing. Always they will ask in the dip in the examination, the dip due to the reason, that is the wind shear and your aspect ratio. So not reason for the wind drag or simple air resistant or simple atmospheric air resistant. Please, this option also they will give in the exam, but this is not the option. So only the due to the wind shear. Shear is, you know, that the force per unit area, the shear. So that is your shear, and the aspect ratio, that is your ratio of your depth to width of the channel. And if you represent this type of your velocity in this channel, so now take the rectangular channel or any triangular channel, trapezoidal channel. If you draw this velocity curves for a more in a open channel, like another section for another, so this is called your isovels. The section or contours line equal velocities in different shapes for your natural section, that will give isovel, mean the equal velocities. The velocity like as shown in this picture, that give the equal velocity, we can call the isovel. So now based on this condition of a different depth, from the different depth the velocity may be vary, as I told you in the isovels. So these for the average at a single point, average at single point in the surface of the top, that is called your point 2 into depth from the top to down. So that is, we can write this average velocity at single point, some constant into velocity at surface, that is k is varies, that is your 0.8 to 0.9 depends upon your channel section. And for the 2 points for like river, for any canal, we can estimate at the 0.8. So that is at this section here 1, and at the 0.8. Suppose assume this is the total 1 meter. So now this is 1 meter, this is the 0.8 meter, this is the 0.6 meter, this is the 0.4, and this is the 0.2, like this. So in this condition, if we want to measure the velocity at 2 points, now we can say the average is 0.2 and 0.8 we can take. Here the velocity is some constant into surface velocities. This constant can be represented in 2 ways. Okay, we'll discuss in the upcoming sessions. For the wide rectangular channel, or so now the depth to width to depth ratio may be different. So for the wide channel, the depth will be insignificant. So that is the aspect ratio B by Y more than your 5. Please remember, this is the question they will ask in the examination. And this wider section, the bit a little bit below. But same thing, the maximum velocity in the narrow channel, it is lower than your wider channel. So here in this condition, the aspect ratio, that is width to depth, is lesser than equal to your 5. So that is the difference between your wider channel and your narrow channel. Please remember, this is the 2 major difference. Next, this velocity distribution in this open channel will always depends on your shape, roughness, alignment, and slope of your channel bed. That is your shape of means which shape, whether that is a channel is circular, triangular, or trapezoidal. Roughness. So suppose the channel is rough. So how rough? How whether it's line channel or unlined channel. Okay, that is called your roughness. That nothing but your internal frictional resistance offered by the channel bed. Alignment. Alignment means, so these are the alignment, how the channel is aligned. And slope of your channel bed are graded, nothing but, so the how much lang slope. So here the slope is called your reducing, again the slope is increasing, again the slope is reducing. So now this is called your adverse slope. The slope is increasing towards your direction. Here the slope is reducing. So that is called your gradient slope. So here gradient is again reducing. So here gradient is increasing. So like this is called your slope of your channel. All the parameters will affect your velocity profile in your open channel. So now as I told you, the average velocity of average is some constant into your velocity surface. This constant can be represented in the 2 ways. That is called your energies, kinetic energy, and another is momentum energy. So the kinetic energy or energy coefficient are also called as your Coriolis coefficient alpha. So this one type of energy coefficient we can add. Another is your momentum equation or Bosnius coefficient. So these are two types of the coefficient we add to get the maximum or correct velocity. That is when the variation of the velocity across your section is high, we need to apply some corrections to compute the value of energy and the momentum. So those computation, this correction is called your kinetic velocity and momentum velocity. These values always more than your or equal to your 1. So this alpha is more than your beta and beta always more than your 1. Or for the practical purpose, we can assume this value is equals to 1. Now similar way, now in this canal, whether rectangular, trapezoidal or triangular, so how the pressure distribution is taking place. So in this condition, in the rectangular, how the pressure distribution is there. When the depth is, we know the pressure is always directly proportional to your head. The pressure is increases, the head is increases. Nothing but the head always, the depth is always increases, pressure is increases. Similar way, in this condition, when the channel having the very small slope, that is the theta always lesser than 10 degrees. In this condition, we can say that this is the diagram. At the bottom, the pressure is high. This is the water surface. Act upward for this cross section area, P into density area, change in area, and due to weight of your water, we can write the density depth into area, that will act downward. Similar way, we can say this, balance these two equations, that the weight of the water and the pressure will always move upside, and simplify the equation, we can get the pressure equal density gravity into height. This is the y mean nothing but your height h here. So now here this pressure into gravity is always, we can write this specific weight. So now we can say that in this condition, the piezometric head at any point in this channel will be equal to your water surface elevation. Hence the ideal gradient line in this small slope angle channel will coincide with your water surface. And the pressure is always equal to your atmospheric pressure, density, gravity, height. And these are the P directly proportional to your head. Similar way, when this channel with slope is increasing more than the 10%, in this condition, now the channel is very slopy. Okay, in this condition, this pressure may be vary. So that pressure, if you see the slope of the channel is vary, that is more than 10 degrees, then the component of the weight of the column acting along the column, see this is your weight of the water acting downward. So that is your weight D into area. How much? That is same thing, nothing but your specific weight, density, gravity into change in area, and this angle. How much? So this angle, because with respect to me, we can always take the normal depth. This is the depth. So we can write that is your cos theta. So that is your cos theta. And the force acting at the bottom and the water force acting upward, that is your nothing but pressure into area. And the pressure is equal to force per area. So now I need the force, that is P into area. So now the force acting downward and force acting upward both are same. So now if you simplify this equation, we can get the pressure. So now it will indicate when the theta angle is increasing. So in this condition, the pressure also be varies. So the hydraulic gradient line does not coincide. So in this condition, the hydraulic gradient is sum of your z plus your y, that is your normal depth. So that is the case here. Okay, in this small slope, the pressure equal to atmospheric pressure. That is, in this condition, the hydraulic gradient line is coincide with your water surface. Whereas in the slope of the channel more than 10 degrees, in this condition, the pressure is not equal to your atmospheric pressure. In this condition, the hydraulic gradient line always is below the free surface.